Alright, let's look at Kirchhoff's law. He has two laws of electricity. The first law, also known as Kirchhoff's current law, stems from the conservation of electric charges. So what does this law say? It basically says that the sum of the current entering a junction must be equal to the sum of the current leaving that junction. So the summation of current at the electrical junction must be equal to 0. So allow me to explain. If I have a current I1 entering a junction here and a current I2 entering the junction as well, and I have a current I3 leaving the junction and a fourth current I4 leaving the junction. So what this law states is the sum of the current entering that junction, which in this case is I1 plus I2, is equal to the sum of the current leaving the junction. In this case is I3 plus I4. So this is Kirchhoff's first law, also known as Kirchhoff's current law. Let's look at the second law. The second law is also known as Kirchhoff's voltage law. So this voltage law stems from the conservation of energy. So what does this law say? It says that the sum of potential rise in an electric circuit loop is equal to the sum of potential drop in that same loop. So allow me to explain. I have here an electrical circuit with two loops. So this is the first loop, this is the second loop. So I'm going to call this E1, E for EMF, E2, this is R1, R2, R3, and the current flowing in the first loop is I1. The current flowing in the second loop is I2. Notice that the current entering R1 is I1. The current entering R2 is I2. Now notice also for R3. This resistor, the current entering R3 is not I1, neither is it I2. So for convenience, I assign a current I3. And also for convenience, I randomly assign the direction of the current flowing upwards. So from here, I can see from Kirchhoff's first law, at this junction J, at junction J, the current entering the junction, I2 plus I3, the sum is equal to the sum of the current leaving the junction, which is I1. So this gives me the first equation for my simultaneous equation later. And let's look at second law, the voltage law. Let's study loop 1. So for convention, I assign a direction. So I assign my movement along this loop 1 to be in the anti-clockwise direction. So the first potential difference I'm going to experience is from E1. So from here, we know that the long line represents plus, the short line represents minus. So as I move across in the direction of my convention, anti-clockwise, I'm moving actually from the negative terminal of the cell to the positive terminal of the cell. So in this case, it's a potential rise. So for loop 1, the sum of potential rise in that loop is equal to the sum of potential drop in that loop. So we have the first potential rise, E1, and as we move along, we arrive at the next potential change. So this potential change is across R1. So what is the potential change here? V, I call this V1, is equal to I1 R1. And we know current flows in a resistor from a higher potential to a lower potential. So this V1 is actually a potential drop. So potential rise for E1 minus potential drop for across R1, which is V1. And the next one, I close the loop, I move here. So here I have another potential drop. This is plus, this is minus. Why plus, why minus? Because I follow the convention of this direction of I3. Current always move from a higher potential to a lower potential across a resistor, in this case R3. So it's actually moving according to my convention from a higher potential to a lower potential. So this is again a potential drop. So I continue to subtract that potential drop, which I call this V3. And I close the loop. I go back to my start point. So this forms a closed loop 1 equal to 0. So this can also be written in a form sum of potential rise in loop 1, which is E1, equals to sum of potential drop in loop 1, which is V1 plus V3. So either way, the same equation holds. So this is my second equation. But of course, we do not leave it as V1 and V3. We generally use the current I1 and the resistance R1 for V1. So it is I1 times R1 plus, for V3 it's I3 R3. So this forms my second equation. And let's analyze for loop 2. So what is this loop 2? Again, assign a convention. In this case, I assign anti-clockwise again. So let's start somewhere. I start from E2. So E2 again, according to my convention, anti-clockwise is a negative to positive as I move in that convention. So it's a potential rise. So E2 is potential rise. And then as I continue down that loop anti-clockwise, I will reach R3. So R3 is based on my convention. The current I3 is upward. So I'm actually moving down from negative potential to positive potential across R3. So this is a potential rise as well. So I add the potential rise, V3. And as I continue my journey in the anti-clockwise direction, I will reach the next one, which is R2. R2, the potential, again, this is from plus to minus because of the convention of I2. I2 direction moves in the direction from a higher potential to a lower potential across the resistor R2. So according to my convention in the anti-clockwise direction, I am entering R2 from the positive to the negative, from a high potential to a low potential. So this is potential drop. So potential drop across here, this is V2. So I subtract V2 equal to 0. So if I rearrange this, I get V2 minus V3. And V2 minus V3, again, I don't leave it as V, I take it as I2 R2 minus I3 R3. So this forms my third equation for further analysis. So in summary, this is Kirchhoff's second law, also known as the voltage law. So let's look at an example here. I have with me an electrical circuit with two loops. Let's call this loop 1, loop 2. And my unknowns are IA and IB. Supposed to calculate what IA and IB are. So I use a convention. My convention in this case is clockwise. Now why do I choose clockwise? Just for convenience, because I follow the direction of my EMF. So I go from positive. So let's see. Loop 1. I start off with, again, my preference is the cell, given 5 volts. So this is potential rise, 5. And as I move on, I notice that for this resistor 30 ohm, I do not have a current. I don't have a defined current, so I'm going to define it as IC. And I point it downwards for convenience, because from Kirchhoff's current law, KCL, I can form at this junction the first equation. So IC is equals to IA plus IB. Current leaving the junction is equals to the sum of the current entering the junction. So for voltage law, I look at loop 1. As I go to the second potential change, which is across the 30 ohm resistor, it is going to be according to my direction of IC, plus minus as shown here. So it's a potential drop. So 5 volt is a potential rise, and then I reach the potential drop, which is 30 times IC. And have I finished? No, my loop continues to the 20 ohm resistor. So 20 ohm resistor, the current flowing, so this is going to be IC, and here I will have IA and IB to complete the circuit. So the current entering the 20 ohm resistor is in this direction, IA. So again, it's plus to minus, and in this case, it's again potential from a higher potential to a low potential is potential drop. So again, I subtract 20 IA, and then I check the loop completes with no further potential changes. So I equate it to 0. So this is my first equation, this is my second equation. Now let's consider loop 2. So for loop 2, we're going to apply a convention. In this case, I take the anti-clockwise route because of my cell. So again, it's from negative to positive. It's a potential rise, so 6 volts potential rise. I enter the 30 ohm resistor. Following the earlier argument, it's potential drop. So I subtract 30 IC, and then I have the next potential change. In this case, following IB direction, it's plus and minus. Again, it's a potential drop across the 40 ohm resistor. So potential drop, I subtract 40 IB, and then I close the loop with no further potential change. So this forms equation 3. So if I may substitute equation 1 into equation 2, I get 5 minus 30 IA plus IB minus 20 IA. I get minus 30 minus 20 minus 50 IA minus 30 IB, and this is equal to 0. This gives me equation 4. I do the same, substitute equation 1 into equation 3. I get 6 minus 30 IA plus IB minus 40 IB I get 6 minus 30 IA minus 70 IB. And rearrange, I get 30 IA equals to 6 minus 70 IB. I get my fifth equation. So I substitute equation 5 into equation 4. What do I get? I have 5 minus 50 over 30, 6 minus 70 IB minus 30 IB. So that works out to be IB would be equal to 0.0577 ampere, and IA is equal to 0.0654 ampere. So with that, I calculated my IA and IB. Now at this point, I would like to add that even if I assign an incorrect direction to the current IC here, it does not matter, because my final answer IB and IA would confirm my direction for IC. Even if I need to calculate IC, it may be a negative value. It just shows that my original assumed direction for IC is incorrect. So it does not matter. So with that, thank you.